Welcome to Spring LIB.
Okay, in this problem, we're asked to look at the kinetic energy, velocity, and stopping potential for photoelectrons being ejected from a metal with a work function of 2.3 electron volts and incident light with a wavelength of 190 nanometers. So this is a photoelectric effect problem, clearly. The one thing that's particularly worth noting is that the stopping potential EV naught is going to simply be equal to the kinetic energy of the ejected electrons. So you can see from the diagram, incident light hits the surface with a particular energy. The surface has a work function phi. If the energy is greater than this work function, we will be ejecting electrons, which will have a kinetic energy. For these ejected electrons with kinetic energy K to come to rest after being ejected, it needs to go through a potential difference of equal to K. So that's one thing worth noting. Taking a look at the equations, we'll need to find all the quantities. We can start with the principal photoelectric effect formula, K equals HF minus phi. So in other words, the kinetic energy of any ejected photoelectrons will be equal to the energy of the incident light minus this work function energy. Now in this problem, we don't know the frequency of the incoming light. However, we do know its wavelength. We can actually get the frequency of the incoming light using the equation C equals lambda F. So we can actually convert to wavelength, which we can use. Once again, the kinetic energy of the ejected photoelectrons must be equal to the stopping potential in order to bring these to rest. That's key. And of course, we know that that kinetic energy is proportional to the mass and proportional to the square of the velocity for any particle with mass. So some constants we'll need for this problem. We'll need the speed of light, which is approximately 3 times 10 to the 8 meters per second. We will need Planck's constant, and it will be useful to use electron volts in this problem. So Planck's constant in electron volts seconds is 4.136 times 10 to the negative 15. And of course, we have the charge and mass of an electron, 1.6 e to the negative 19 coulombs, and mass 9.11 e to the negative 31 kilograms, quite small. Okay, so let's jump into this problem. So starting off, we can use the equation for the photoelectric effect, K equals HF minus phi. We know what phi is. We can reformulate this as K equals HC over lambda using our relationship C equals F lambda. So now these are all quantities we know, so we can actually do the calculation. So using electron volt values, 4.136 e to the negative 15 electron volt seconds times 3 times 10 to the 8 meters per second. All of that over our lambda, which in this case is 190 e to the negative 9, 190 nanometers. And of course, subtracting from this whole quantity the work function, which is for potassium, is 2.3 electron volts. Doing this computation, this big quantity here, which is the energy of the incoming light, comes out to be about 6.53 electron volts. Of course, subtracting the work function, we are left with a result of 4.23 electron volts. Great, so this is the kinetic energy that each photoelectron will have after being knocked out of place from this metal due to the incoming light. And to stop this, we have to remove all this kinetic energy, which means any stopping potential must be equal to K. So it's not very interesting. Our stopping potential will also be 4.23 electron volts. Not too interesting. So let's figure out what the velocity is for these electrons. We know, of course, that kinetic energy is 1/2 mv squared using mass and velocity. So now we can solve for V first of all. V is going to be simply equal to the square root of 2k over m. Now, when we actually do this computation, we have to be careful because we have our kinetic energies in electron volts and our mass in kilograms, which are not going to merge well. So we actually need to convert back from electron volts to joules using the relationship 1 electron. Well, I'll write it in the actual computation. So let's plug all this in. Here's our 4.23 electron volts. And to convert, we need to multiply by 1.6 e to the negative 9 joules per electron volt, which is just a conversion factor. J per EV. Got to extend the square root a little bit. And then the last thing we need is the mass of the electron, which is 9.11 e to the negative 31 kilograms. Doing this computation gives us a result of 1.23 times 10 to the 6 meters per second. So these are the velocities of our photoelectrons. These are the energies of our photoelectrons. And that amount of kinetic energy needs to be equal to the stopping potential. Oh, actually, small mistake. That 4.23 electron volts is our total. That should not be an equal sign. So that's the problem. We have energies of our photoelectrons equal to stopping power to take that energy away, and the resulting velocities. So those are all the parts of the problem that need to be accounted for.